Welcome to my Connecting Networks Cisco review. Here dealing with Chapter 3, Point-to-Point Connections. In this chapter, we're looking at serial point-to-point. We're looking at PPP operations, how to configure it, and troubleshooting the WAN connectivity using PPP. Our objectives is to explain the fundamentals of point-to-point serial communications across the WAN, look at things like PPP, look at things like HDLC. We're going to talk about how to use PPP within a session, how to establish it, its encapsulation, its authentication, how to troubleshoot. PPP is always the easiest one. It's point-to-point protocol, and it's I wouldn't want to say a serial connection, but it is a very simplistic protocol used for tunneling. It's one of the things. So point-to-point connections are used to connect LANs to service providers through a WAN. This is also referred to as a serial connection or some type of leased line connection. Communication across a serial connection is that methods of transmissions. It's basically sending data through a service provider's network that is a serial connection. This is done in parallel. Bits can be transmitted simultaneously over multiple wires. Serial connection, more specific serial communication, comes in three major flavors: RS-232, V385, and HSSI. On the WAN link, the data is encapsulated by the protocol used by the sender. So if our sender is sending it as serial, then it'll be encapsulated as serial. If it's being sent via V35, it'll be encapsulated that way. The receiving router uses the same communication protocol to de-encapsulate the frame as it arrives. Point-to-point links can connect two geographical areas over a greater distance. Carriers dedicated specific resources, for example, like a leased line, a T1, a T3, things of that. Point-to-point protocols are more expensive than shared services, but they're dedicated links. So one way that we deal with our serial communication is with time division multiplexing. And part of that is multiplexing is the scheme that allows multiple logical signals to share the same physical media or same physical channel. Basically, time division is we will sparse out time, and each section gets an X amount of time on that wire. Here you're going to notice everyone gets one packet, and then it restarts. So it goes voice, video, data, and voice, video, data, and so forth and so forth. Then it'll be demultiplexed and put back together. So it has to be multiplexed, sent over the wire, and then reconstructed. Statistical time division multiplexing will actually take and look at, well, what is sending the most? And it will then carve out that time slot based off of the available channels. That way, the items that are the most critical get more time on the wire. Time division multiplexing examples could be things like a SONET. That's going to be the synchronous optical network fiber. Or even things like SDL, SDH, which is, again, more for optical transports. Here we're looking at traffic arrived at a given SONET multiplexer from one of four places at a 2.5 gigabit speed as it goes out a single stream of 10 gig. We have what's called a demarcation. That's always a good term because we should have learned about this way early on. A demarc is the point where the ISP is responsible up to, and then the business becomes up to. Within the United States, typically there's a demarc on a building, and that's where the ISP is responsible for. Where in other countries, that demarc could be a different location. Since we're dealing with serial, since we started off with serial, we have a DTE and a DCE. So one side of the cable is DTE and one side is DCE. Commonly, the DTE is going to be a common CPE, normally a router, and could also be a terminal type computer or other device. The DCE is commonly a modem or a CSU/DSU unit, and it is the device used to convert the user data from the DTE into a form acceptable on the WAN. Typically, the DCE controls the clock. Here is a serial connection. In all honesty, I've not really dealt with many serial connections. I use it heavily within the training environment, but in real world, not as frequently as it would seem. Bandwidth for the appropriate lines. Here we have T1, T3, 56K, and then we have the appropriate OC or octal connections. Not OC is not octal. We have the OC fiber optic connections 1, 3, 9, so forth, so forth, so forth. WAN encapsulation. Depending on the media, depending on the protocol, different communication encapsulation will take place. If it's a leased line, it could be HDLC, PPP, or SLIP. If it's a telephone company or a circuit switch connection, again, it could be HDLC, PPP, or SLIP. However, in a more modern day network, if it's a packet switch network, we're looking at things like frame relay or ATM or X25. There are different technologies at the WAN level. So the first one is going to be the HDLC. It's a bit-oriented synchronous data link layer protocol, which was developed by the ISO. Uses synchronization serial transmission to provide error-free communication between 2 points. HDLC defines a layer 2 frame structure that allows for flow control and error control through the use of acknowledgements. Cisco has developed an extension to the HDLC protocol to solve the inability to provide multi-protocol support, which is the Cisco's HLDC. Here is the frame type. You'll notice it will have a control type, both for information frames, for supervisor frames, or an unnumbered frame, also known as an I-frame, S-frame, or U-frame. The U-frame supports control purpose as are not sequenced. The S-frame is provided control information, request and suspended transmission, also reports on the status, and it will acknowledge the receipt of an I-frame. Then we have an I-frame, and this will carry upper layer information and some control information, and it will send and receive sequence numbers and the pull final bits performing the flow and error control. There is a specific sequence to initiate it, which is an 8-bit flag, 01111110. How do we configure it? Underneath a serial interface, you type encapsulation HDLC. The default encapsulation method used by a Cisco device on a serial link happens to be a point-to-point. So connecting to a non-Cisco device, synchronous PPP is going to be more important. Troubleshooting may also be looking at both ends to see what each side is set to. looking at the interface and the controller will show the appropriate encapsulation type. Is it encaps HDLC? Is it encaps V35? So forth. So some basic troubleshooting is going to be if the serial connection is up and the protocol is up, then we're good. But if the serial is down and the line protocol is down, and it's assuming it's the DTE mode, it could be that the router is not sensing the time. Check the LEDs, verify cable, verify issue the connection, double check ISPs doing the appropriate timing, so forth. If the serial is up but the line protocol is down, the clock rate interface configuration command is missing. On the other end, verify that clock rate is issued and make sure that the clock rate is set to the appropriate speed. If the line is up and the protocol is up, but it's called loop, a loop exists in the circuit. The sequence numbers in the keep alive packet change to a random number when the loop is initiated. So we're going to double check to verify loopback interface. Sorry, we'll do a show run to look at any loopback interfaces. If there is a loopback interface, configure the command to use no loopbacks, because within the HDLC loopbacks enter some issues. Last, X is up, a protocol is down, it's disabled. Typical reason is there's a higher error rate. Could be a loop, could be many things. But here we're looking at maybe bad hardware, a CSU, DSU issue, things of that nature. Serial X is administratively down, line protocol is down. That's because the shutdown command was issued or the no shutdown command was not issued. So that gives us a brief overview of the HDLC. Moving on is the more common PPP. So PPP does use something similar to the HDLC-like encapsulation, but it also has what's called a link control protocol and a family of network control protocols. So again, the HDLC protocol for encapsulation, the extensive link controller protocol to establish, configure, and test data, and for data link connection, and the family of network control protocols to establish, configure the different network layer protocols. That's going to be the different layer 3 protocols, IPv4, IPv6, AppleTalk, so forth. You notice how old this is because we're talking about AppleTalk, Novell, IPX, SPX, and SNA control protocols. Advantages of PPP, it's not proprietary. It includes many of the features not available in the HDLC. It does support both CHAP and PAP, so that there are some authentications. Even though PAP and CHAP are both fairly old and aren't really secure anymore, the LCP sets up the PPP connection and its parameters. The NCP handles higher layer protocol configuration, and then again the LCP will terminate that PPP. The higher layer is going to be again the different layer 3 technologies. The LCP provides automatic configuration of the interfaces at each end, and handling packet size, common error correcting for basic misconfiguration, terminating the link, and it will also help with determining when a link is functioning properly or if it's failing. The NCP will permit multiple network layer protocols to operate on the same communication link, and for every network layer, protocol that's used, PPP will use a separate instance of the NCP. So if we're dealing with both IPv4 and IPv6, we can do that with the same communication link, but we'll have two separate NCP functions there. The PPP frame will look like this. So how do we actually initiate a PPP session? First, phase 1, the LCP must open the connection and negotiate the configuration options. It will complete when the receiving router sends the configuration acknowledgement frame back to the initiating router. LCP will test the link to determine whether the link quality is sufficient to bring up the network layer protocols. After the LCP has finished the link quality, then it will hand it off to the NCP, which will then separate configuration for the network layer protocols and then bring them up and then take them down when necessary. Go into the LCP operations. LCP operations include provisioning of the link establishment, the link maintenance, and link termination. That operation will use 3 classes of the LCP frame to accomplish this. Those frames will include the link establishment frame, the link maintenance frame, and the link termination frame. During the link maintenance, LCP can use messages to provide feedback and test the link. Echo request, echo reply, discard requests will be used for testing. You can also have a code reject, protocol reject commands, and they will provide feedback when the devices receive an invalid frame. Here we have the termination process. We have the initial configuration, the data exchange, and then we end with a termination request and a terminate acknowledgement. When we're looking at the LCP packet, underneath the data, we'll have an LCP subpacket, code, identifier, length, and the variable data. So the code will be broken up into 6 different sections. Multiple different sections, not just 6. Configuration request, configuration acknowledgement, configuration NAC, configure reject, terminate request, terminate acknowledgement, code reject, protocol reject, echo request, echo reply, discard request. It will have 11 different LCP codes. Let's talk about configuration options, more specifically authentication. Again, the authentication used by PPP is PAP and CHAP. There's also a compression function that can also be used multi-link that will combine multiple channels to help increase bandwidth. NCP, once the LCP configuration is negotiated, then we have an NCP request and data exchange, and then again a NCP terminate sequence. How do we configure PPP? Well, we need to, We need to look at 5 things: authentication, compression technology needed, error detection that will identify the fault conditions, the PPP callback, and that will be used for enhanced security, and multi-link options. Most simplistic is encapsulate PPP, both sending and destination. If we're using a compression, we need to go ahead and do that here. Compress, and one of the keywords, predictor or stack. After that, the PPP quality, which will then be PPP quality and a percentage number. The PPP quality percentage command ensures that the link meets the quality requirements, If the quality is not meeting that requirement, the link is closed. So you can provide some type of quality assurance. Multilink commands, you can have multiple link groups, which is just PPP multilink, and then you link it to a group. And then those groups are then assigned for multiple interfaces. Verifying, show interface serial, show interface, show PPP multilink will be the typical show commands. Here is the show PPP multilink, so you understand kind of how it works, both on the sender and destination side. Moving on is the authentication portion. Again, we can do PAP and CHAP. PAP is a two-way handshake. CHAP is a three-way handshake. The initiating PAP will send the username and password, and then the destination will verify and then accept or reject it. The CHAP will do a three-way process. There will be a challenge, a response, and then a accept or reject. So the challenge will come from the destination. The source will then respond with the appropriate username and hash value of the password. And then the destination will either accept the hash value or not. There is a flowchart for the encapsulation and authentication process. Authentication then will flow into if it's valid or not. How do we set up the authentication? It will be PPP authentication, the appropriate authentication type. If it will use one or both, don't forget that since we're using PAP, it will be sending a username and password. Same thing with CHAP. So PPP authentication PAP, PPP PAP, sent username R1 and password. And then the destination would have to have the same appropriate password. You'll notice here the username will be R2, even though we're dealing with R1. That's what we're going to be sending to R2. On R2 side, we'll be sending the username R1. So let's make sure we get that. This is R1. This is the username and password we're sending to R2. And then this is what R2 is going to be sending back to us. So you'll notice these guys are going to match. There. CHAP, same thing. Moving into our last major section is troubleshooting. You can debug PPP. You can look at packets, negotiation, errors, authentication, compression, and the CDCP, or the display of the protocol errors for it. Debug PPP. Authentication will focus on the authentication errors. PPP packet will show you the packet errors, negotiation, errors, compression. Each one of those will show you specific errors. Debug PPP, what do you want to look at? And that is the end of this chapter. We only really looked at two of our point-to-point connections, HDLC and PPP. If you have any questions, please let me know. Thank you.